this week, you want to see my notes, which are on the PolyLearn site, and then I'm showing you right here. But basically, we're going to take the variables in each of our equations from f equals ma, and we're going to perturb the variable and then multiply it out with the trig identity, just like we did before. All right? And when you're done, you'll end up with forces that are shown as shown here. And we're going to create dimensional stability derivatives out of 1 over m delta x, 1 over m delta y, and 1 over m delta z. These are going to become dimensional stability derivatives, right? And we'll practice today doing 1 or 2 of those. You to know how to get those dimensional derivatives from the dimensionless coefficients that are in this book. So I could give you an airplane from Nelson's book or from Roscom's book and then ask you to compute the dimensional derivatives that go into those equations of motion. That's what's done when you build a flight simulator. Same thing. Okay. So that's one thing you have to know how to do is how do I get these dimensional derivatives that belong in this 1 over m delta x, 1 over m delta y, and 1 over m delta z. The rest of these variables just fall out from the math. And on the right side of the equation, the motion side, when you perturb the matrices, you get a fairly complicated set that looks like this. And again, if you want to work these out, you got spare time, fine. Part 2 of this class, part 1 was the tools, math tools. Part 2 of this class was the airplane in equilibrium. We built equilibrium, steady state flight, trim charts, right? Tail scraping, stall. How much CG do we allow? Right? How big should the tail be? How can we get the tail small? That's part 2 of the class. All really important things for arrows. Part 3, we're perturbing about equilibrium. We have perturbations about equilibrium. The airplane is going to oscillate about that equilibrium, some delta perturbation. So I'm going to add the perturbation to the steady state solution to get the full solution, if I was going to do a flight simulator, for example. Right? So another example, when I went to work at NASA Dryden, my first year here, I went to work in the summer, and I wanted to build a throttles-only flight control system for 707, right? The first thing I had to show that my linearized equations overlaid the actual airplane in the flight simulator. So they do a perturbation of the flight stick in the flight simulator to get strip charts would come out. And then I would have to show that my pulse input overlaid that curve. Then they would believe that my model was good, right? That I didn't make a mistake when I made my perturbed model. The linear equations that I get for perturbed, I had the full power of the root locus and the Bode plot and the loop shaping. I had the full power of all the analytical tools that are denied to the nonlinear people. If you're going to solve a nonlinear control problem, right, then it's a trial and error approach, or each solution is unique to that particular problem. But when you're solving a linear control problem, then you have a whole set of tools universally open up to you. That's why we linearize these sets. But the control laws we build, when we finally build the control laws, they'll work fine with MATLAB. We put them on MATLAB. Look how great MATLAB has got my control law. But then you're going to take that control law and what? Put it back in the non-linear airplane. And it's not going to work so good. It just won't. So you'll have to tweak it. You'll tweak it. And if you do it reasonably slow and get some experience with it, as you tweak your control law, you'll get one that's more and more acceptable. So the controls design is an iterative process. You make your first cut based on estimates for stability derivatives, estimates for your perturbed models. You build your control, then you put your control law in. MATLAB says it's going to work fine. Then you take that and you put it in the airplane or in the flight simulator and you fly it. Look at equation X and Z. Equation X and Z, when you expand, that's drag. X is drag and Z is lift. So if you look at the motion variables over there, the motion variables tend to be those variables that keep you in the aircraft's vertical plane. They tend to be. So the Y equation now tends to have only R's and P's. See, it only has things that move the vertical plane. So we're going to see that with the next set of equations, the same thing is going to happen, and then that's going to allow me to separate these equations into two sets. The first set of perturbed equation is just going to allow me perturbed motion in the aircraft's vertical plane. And the second set of equations is going to allow me perturbations when I'm just moving the vertical plane. So we call this first set longitudinal perturbed equations, and we call the second set the lateral perturbed equations. So there's your lateral equation, LMN. That's the torque equations. And there you can see the dimensional derivatives are going to be over on the right hand, that top there in equation 42. Those are the dimensional derivatives. And then the right-hand side is going to expand by the perturbed motion variables. And then you'll end up with equation 45. When you get rid of the steady state terms, you'll end up with equation 45. And under straight and level conditions, you end up with equation 46. For equations 46 through 49. And so these equations 46 through 49 are what you see in textbooks for the lateral equations. Notice how I've separated the motion variable. I've divided through by x, jx, jy, and jz, so that I isolate that. And that's, you have to do that in order to get your dimensional derivatives, right? So these dimensional derivatives in this expansion over here are divided, normalized by the respective moment of inertia in each axis. I put those together, side force, roll, and yaw, and I just say that those equations are independent of the other three. So I only deal with those three equations at a time. Then I say the equations for x, drag, z, lift, and moment, m, are independent of the lateral ones. The forces and the moments don't couple. This whole half-hour spiel that I've given you so far, if I had to summarize it in one line, I'd say, where do transfer functions come from? They come from separation of these perturbed equations. Right? The equation, the lift equation, and the moment equation, and put them together. I notice that they all are functions of variables airspeed, w, and theta. W is vertical velocity, or alpha. You can think of W as alpha, angle of attack. So if I pull this in matrix format and pull out the U, W, and theta, if I pull them out, I'll get a matrix equation with my controls, elevator and throttle, and this matrix equation will show up from the longitudinal equations. This is basically the heart of 420 in 20 minutes. Right? We've taken all the F equals ma and the torque equals j omega dot, all the Newton's equations. We've expanded them in dimensional derivatives, perturbed them, separated them to longitudinal and lateral axis, and there's the longitudinal set right there. From now on, we're going to start with that. So how would I solve for the transfer function, for example, of airspeed to elevator? How would I solve for that using Kramer's notation? Well, the first thing you do is take the determinant of the full matrix on here on the left. You take that determinant. And you see you can end up with like a fourth order system with an S. You see that? If you took that determinant, I assume you had determinant somewhere. Right? So you take that determinant. That becomes your denominator. Well, if I'm solving for airspeed to elevator, then I replace the airspeed column with the elevator column. If I'm solving for airspeed from elevator, I replace the airspeed column with the elevator column, and I call that another determinant. And that determinant is called the numerator, airspeed from elevator. It's another 3 by 3 determinant. The ratio of those 3 by 3 determinants is the transfer function relating u to del E. You see the nice power of the simplified notation? I got a 3 by 3 determinant here in S, a 3 by 3 determinant here in S. It would take you a whole period to write that thing out, fourth order. So we let MATLAB do the work. I just want to know that you understand what you're doing. Do you see something common in those solutions? The del log never changes. They're the product of these two roots. There's 4 of them. So those 4 roots, if I were to plot them, always, for a conventional looking airplane, end up like this. There's 2 of them. The roots always stay the same no matter what transfer function I pick. The zeros are going to change. Therefore, the root locus is going to change. depending on what I decide to close my loop on, the root locus. Look like? I'm flying along, and let's suppose we're looking at the theta. We're looking at that, and I give a little pulse in the cockpit, I pulse the stick. What's going to happen? These roots are they fast or slow? Which of these roots are fast? Which ones? These are fast. Why? Because they have a higher omega D, don't they? So these are the fast roots. They also die out faster, right? Right? The sigma is higher. So I have the envelope of these roots. So when I pulse the stick in the cockpit, the short period is going to go like this. Right? It's going to die out. Like that. Phugoid roots, on the other hand, the phugoid roots are going to be much slower. So after my short period dies out, the phugoid load has just been excited. And it's going to airplane stick of bouncing oscillation, and then I'll have this slow exchange. Now what physically then is causing these roots? Well, physically what's happening is that the short period motion is caused by the angle of attack at the tail by CM alpha. The slow phugoid is an exchange of kinetic energy with potential energy. No, kinetic energy, potential energy. Kinetic energy, potential energy. That occurs very slow, as exhibited by these roots. The CM alpha springing, because of the center of gravity position, and CM alpha wanting to return it, is much faster. You have it.